A wire which passes through the hole in a small bead is bent in the form of quarter circle. The wire is fixed vertically on the ground as shown in the figure. The bead is released from near the top of the wire and it slides along the wire without any friction. As the bead moves from A to B, the force that it applies on the wire is, we have to check the direction of the force, whether it is radially inwards or whether it is radially outwards or whether it changes direction after certain angular displacement. So if we consider the motion of a small block over a sphere, consider there is a small block over this sphere, and if we release it with negligible velocity from the top, then initially when its velocity is very small, so the normal reaction will be outward, and after certain angular displacement theta, let us say, what are the forces acting on this block, small block? The weight of the block mg, a normal reaction radially outward if the velocity is small, and it will gain certain velocity v when it will fall down certain distance from the vertical. So let us say this velocity is b. Initial velocity of projection is 0. So what is the fall that it has achieved? This is the fall, and if the radius is r, then it can be proved that h is nothing but r into 1 minus cos theta. So if we apply work energy theorem between the initial position and the position at an angular displacement theta, then we can write v square equal to 2gr 1 minus cos theta. Let us call this equation number 1. And if this angle will also be theta, and the component of mg in the radial direction towards the center will be mg cos theta. mg cos theta. So if we write the equation of centripetal force at this instant, the centripetal force is the force towards the center, so this will be mg cos theta minus m, and this should be equated to mv square by r. So m by r, and v square is 2gr 1 minus cos theta. So this r gets cancelled, and if after rotating certain angle theta, we we can tell from experience that the block, once it gets certain velocity, sufficient amount of velocity, then it will fly off the block. Now when it flies off the block, the normal reaction becomes 0, and when the normal reaction becomes 0, if we cancel mg on both sides, we get cos theta equal to 2 minus 2 cos theta, or we have cos theta equal to 2 by 3. 2 by 3. So this implies the value of theta is cos inverse 2 by 3. That means after rotating an angle equal to cos inverse 2 by 3, the block will fly off. That means the normal reaction will become 0. So initially when the block starts, let us come back to the original diagram. When the block starts and the angle rotated is small, the normal reaction will be outward. The normal reaction will be outward, and when it rotates an angle theta that is equal to cos inverse 2 by 3, the normal reaction becomes 0. And since there is a tendency to fly off, to keep the circle, to keep the bead inside the circle, the normal reaction must act inwards towards the center along the radius. So we can say that initially when the angle theta is small and the velocity of the block is quite small, the normal reaction is outward, and after cos inverse 2 by 3 angle, the normal reaction becomes inwards. So the correct option should be option C. Radially outwards initially and radially inwards later. So that's it.